Good morning everyone. So now let us go with the continuation part. Today in this video I am going to say about these types of solvents and also the limitations of Bronsted-Lowry and the Lewis acid-base theory. Firstly, what are the types of solvents? Solvents can be broadly classified into four types based on the tendency to accept or release the protons. So first type is protophilic, which has a strong tendency to accept the protons. For example, H2O, ROH, ROR, NH3, where this R is nothing but a variable group where we can substitute mostly methyl. Next is the protogenic, where it has the tendency to release the protons. Examples are H2O, HCl, CH3COOH, NH3HF. Amphiprotic. Amphiprotic are the solvents. Amphiprotic solvents are the solvents which release and even they take and even release the protons. Examples are mainly three: NH3, H2O, CH3COOH. What are aprotic? Aprotic solvents are nothing but they do not release and even take the protons. For example, CCl4, C6H6, liquid SO2 and also CS2. Next, now let us move on to the limitations. So first limitation is that it was even the common limitation of the same like the Arrhenius, where here even we can't say whether it is an acid or a base unless and until it participates in the reaction. And the second limitation is that some acids and bases, they do not have any proton transfer, but they behave like acids and bases. Like for example, SO2 plus SO2, their electron pair transfer take place, and there it will form SO plus 2 plus SO3 minus 2. So here without any hydrogen or H plus ion or no proton transfer only, some substances they will be acting like acids and bases, and some substances they do not release protons but they have acidic nature. It was the same exception. These are all the same exceptions of the Arrhenius, and they were even repeated out here. And one more is that some substances they do not accept the proton but they have basic nature. So these were the examples. Now the final note of this Bronsted-Lowry theory is that all Arrhenius acids are Bronsted-Lowry acids, but all Bronsted-Lowry acids are not Arrhenius acids, and all Bronsted-Lowry bases are Arrhenius bases, but all Arrhenius bases are not Bronsted-Lowry bases. This is a thing to be remembered. So now let's move on to Lewis theory, Lewis acid-base theory. Firstly, what is a Lewis acid? What is a Lewis base? So Lewis acid, it is nothing but an electron pair acceptor, and electron pair acceptor we call it as electrophile, and which is actually electron deficient species. Now if you see what is a Lewis base, it is nothing but electron pair donor, and even we call it as nucleophile. And these substances they have more nuclear power, more nuclear charge, and these are electron rich species. For example, BF3 plus F minus. F minus means we can take that as 2 electrons are present, and so it will form BF4 minus. And as it accepts the electron, we call this BF3 as an acid, and as F minus it will donate the electron, we call it as a base. And NH3 plus H plus, it will form NH4 plus, where H plus is accepting the electrons. So this is a base and this is an acid now. And what is neutralization as per Lewis? It is nothing but the formation of coordinate covalent bonds or adducts or both acidic and basic nature between acid and base within a neutralization reaction. And types of Lewis acids. Molecules which have incomplete octet. They have the tendency to take the electrons and get their octet even. So let's see the electron deficient species like the BF3, boron trifluoride. Boron trifluoride, there we do have only we don't have more electrons since we have two already, 1s2 and 2s2 2p3. So only 2s2 2p1 will be there, and that's why if and so it goes into the excited state even, there will be only 3 valence electrons, and those 3 valence electrons, if they combine with fluorine, then they would just form 6 in the outermost shell. So it is electron deficient species. So in the same way, all the nitrogen group elements like that. So BF3, BCl3, Bi3, AlCl3, BeCl2, LiCl. LiCl, it has only a single bond there, and it has only 4 electrons completely also. And for example, now if we consider how to calculate the acidic character, which has more acidic character, SO2 and SO3, in between them, how is the acidic nature? The acidic nature, it is more in the case of SO3 rather in the case of SO2. Since the effective nuclear charge of the central atom will be increased in the case of SO3. And now an exception case of the above rule, it is nothing but BF3, BBr3, boron iodide. So Bi3 will have more acidic nature than that of BBr3 and than that of BF3. And BF3 has the lowest in the case of halogens. That too, whenever these halogens combine with boron, this is just an exception case, which may be a thing to be remembered. And now, molecule with central atom having only d orbital, empty d orbitals. The molecule that has central atom with empty d orbitals. For example, SiFX4 and GX4. Here X case we can take fluorine, chlorine, bromine, iodine. And SiX4, GEX4, TiCl4, PX3, SF4, AlF3, SnCl2, AsF5, and even XeF6, etc. Now cations. All the cations, they behave as Lewis acids. And cations that have noble gas configuration, they have little affinity for taking the electrons. For example, Na plus, Mg plus 2, Al plus 3. While even some simple cations even will be having more affinity. H plus, Ag plus, Cu plus 2, Fe plus 3. They have more affinity. And strength of acids in the case of simple cations can be taken as strength of this acid. It increases with the increase in the positive charge, and decrease in the ionic radii and increase in the electronegativity. Or increase in the effective nuclear charge. And even molecules of central atom which are linked with more electronegative atom by double bond, then there also we consider that as an Lewis acid. So we can take the examples like SO2, CO2, SO3, etc. And elements which have an electron sextet like the oxygen and sulfur, they accept electron pairs from the Lewis bases and complete their octet even. And where they would complete their octet. Now let us just move on to types of Lewis bases. So here molecules having lone pair of electrons. Molecules that have lone pair of electrons, we consider them as Lewis bases. Lone pair of electrons will be helpful to donate it. So that's why. Unlike some alcohols, amines, NH3, PH3, PCl3, H2O, etc. even. And now all anions, these are Lewis bases. And molecules that have multiple bonds are also Lewis bases. And even halides. Halides, for example, HeF2, HeF4, HeF6, cesium fluoride, NH2 minus, etc. And more electronegativity, then they have more basic character. For example, fluorine minus, F minus is greater than, chlorine minus greater than, Br minus greater than, I minus. And now this is just important, and this is just like an different case. NH2 minus is greater than OH minus, basic nature. OH minus greater than SH minus. NH2 nitrogen, it has smaller atomic ionic radius like that, and that's why here it happens. Now let us just see the limitations and let us just move on to ionic product of water in the next session. And drawbacks of Lewis theory. Arrhenius and Bronsted-Lowry acids are not explained in this theory because they can't accept the electron pairs. For example, HCl, it can't accept the electron pairs as it already has an octet and doublet. HNO3, H2SO4, these are not Lewis acids. Arrhenius bases failed. Lewis theory, it failed to explain the Arrhenius bases. For example, NaOH, KOH, they do not donate any electron pairs. And next, if you see Lewis theory, it cannot classify acids and bases into strong acids, either strong acids or strong bases, or weak acids or weak bases at all. And these are just the drawbacks. And if for the notes, I would like to show. Okay, thank you. Please like, share and subscribe my channel.